Ever wondered how your mobile phone communicates? It all begins with something we call the cellular system. Now, let's dive into the fascinating world of cellular communication. In its most basic form, a cellular system is a network of interconnected cells. Picture a honeycomb. Each of its hexagonal compartments represents a cell in our context. This cellular structure is what gives the system its name. Each cell in this vast network is equipped with its own antenna and operates on a unique frequency range. Now imagine this. You're at a buzzing concert, trying to call your friend who's lost in the crowd. Your phone sends out a signal. This signal is like a virtual flare, shooting up into the digital ether. And who catches this flare? The nearest antenna in your cell. These antennas are like the vigilant watchmen of our cellular world, always ready to pick up signals from phones within their territory. But here's the thing, the antenna is not the end of the line. It's merely the first point of contact. This is where the Mobile Switching Center, or MSC, comes into play. The MSC is like the grand maestro of the cellular orchestra, coordinating all the different elements to make sure your call reaches its intended recipient. It's the MSC's job to direct your call from your cell to your friend's cell. If your friend is in a different cell, the MSC reroutes your call to the antenna in your friend's cell. This rerouting is done so seamlessly that you don't even realize it's happening. It's like passing a baton in a relay race, where the runners are the cells and the baton is your call. And what if your friend moves from one cell to another while you're on the call? No problem. The MSC smoothly hands off the call to the new cell, ensuring uninterrupted communication. So, in a nutshell, your phone talks to the nearest antenna, which then talks to a central system to connect your call. Neat, isn't it? And that, my friends, is the magic of the cellular system, a marvel of modern communication technology. Now that we understand cellular systems, let's delve into how information is actually carried over these systems. Enter frequency modulation and amplitude modulation. Imagine a calm, peaceful ocean. Now, throw in a stone. The ripples that form on the surface of the water are akin to radio waves. These waves, invisible to the naked eye, are the carriers of information in our daily communication. But how does this information get onto these waves? That's where frequency modulation and amplitude modulation come into play. Frequency modulation, or FM, is a bit like changing the speed of the ripples. In FM, the frequency of the wave, or the pace at which the ripples occur, is altered to encode information. The faster the ripples, the more information is packed into that space. This is why FM is often used for music on the radio. The higher frequency allows for a greater range of sound to be transmitted, from the deep bass notes to the high treble notes. On the other hand, amplitude modulation, or AM, is like changing the size of the ripples. In AM, it's the height or amplitude of the wave that is altered to encode the information. The taller the wave, the stronger the signal. This is why AM is often used for talk radio. The human voice doesn't require the wide range of frequencies that music does, so the signal can be stronger and travel further. But it's not just radio where FM and AM are used. Cellular systems also rely on these modulation techniques to transmit voice and data. When you make a call on your cell phone, your voice is converted into electrical signals. These signals are then modulated or altered, using either FM or AM, and sent out over the cellular network to the person you're calling. So, whether it's your favorite radio station or a call to your friend, FM and AM are the unsung heroes making it all possible. But how do multiple calls and data sessions happen simultaneously without causing interference? The answer lies in multiple access techniques. Imagine a highway. There are multiple lanes, each allowing a car to travel without crashing into the one next to it. This is similar to how multiple access techniques work. They allow multiple users to share the same frequency band, much like lanes on a highway, but without causing interference. Now, let's dive in a little deeper. The first technique we'll discuss is frequency division, multiple access, or FDMA. Think of FDMA as a multi-lane highway, where each lane is a separate frequency band. Each user or car is assigned a specific lane or frequency band where they can send and receive data without interfering with others. But what if we run out of lanes or frequency bands? Enter time division multiple access, or TDMA. Instead of assigning each user a separate frequency band, TDMA divides each frequency band into time slots. Each user is allotted a specific time slot in which they can send or receive data. It's like a round-robin game, where each user gets a turn to use the frequency band, and this happens so fast that you don't even notice it. Lastly, we have code division multiple access, or CDMA. This technique is a bit different. Here, each user is given a unique code. All users can send and receive data simultaneously over the same frequency band. It might sound like chaos, but it's not. The unique code assigned to each user helps to separate their data from the others. It's like everyone speaking at the same time in different languages, but you can still understand what's being said because you know your language. These techniques are the backbone of our cellular communication, allowing us to make multiple calls, browse the internet, and stream videos all at the same time, without any hiccups. So, next time when you're on a call while browsing the internet, remember it's the magic of multiple access techniques at work. If you're thinking all this sounds complex, you're not alone. But the beauty of cellular communications is that it's all based on a few simple, repeatable patterns. Let's dig a little deeper. Have you ever wondered how so many phones can operate in the same area without interference? The answer lies in the concept of frequency reuse. Imagine a city, divided into cells like a giant honeycomb. Each cell has its own tower, and each tower operates on a unique set of frequencies. But here's the twist. These frequencies aren't unique to the whole city, they are reused in different cells, following a specific pattern. This pattern is meticulously designed to ensure that any two cells using the same frequency are far enough apart, thereby avoiding any interference. It's a bit like planning seating at a party, ensuring that two people who don't get along are never seated next to each other. In the world of cellular communications, this is how we make the most of the spectrum we have. The spectrum, as you might recall, is a finite resource. Hence, it's crucial to use it efficiently. The fascinating thing about this pattern of frequency reuse is that it's not just used in one city or one country. It's used globally, in every cellular network. This is the key similarity in cellular communications worldwide. From New York to New Delhi, from Sydney to Sao Paulo, the same principles apply. It's like a grand orchestra, each instrument playing its own unique note, yet all coming together to create a beautiful symphony. Only in this case, the symphony is our global network of cellular communications, enabling us to connect, communicate, and collaborate like never before. So, while the world of mobile communications may seem complex, it's really just a game of patterns and repetition. So let's recap what we've learned today. We started our journey with cellular systems, the backbone of modern communication. We learned how cell towers blanket our cities with coverage, creating a network that connects us all. Each cell tower provides service to a specific area, and as we move around, our devices seamlessly transition from one cell to another. This intricate dance of signals keeps us connected whether we're calling our friends, streaming a movie, or navigating the streets of an unfamiliar city. Next, we delved into frequency modulation and amplitude modulation, the two major ways our devices manipulate radio waves to carry information. We discovered how frequency modulation, or FM, changes the frequency of the wave to transmit data, while amplitude modulation, or AM, alters the wave's amplitude. These techniques form the basis of radio communication, allowing us to send and receive information over vast distances. Our journey then took us to multiple access techniques, the methods that enable numerous devices to use the same network without interference. We learned about time division multiple access, where each device gets a specific time slot to transmit data, and frequency division multiple access, where each device is assigned a unique frequency band. These techniques help ensure that our calls and data requests don't collide with each other, keeping our communication smooth and uninterrupted. Finally, we explored the pattern-based nature of cellular communications. We saw how the same frequencies are reused in different cells, a technique known as frequency reuse. This clever use of resources allows for a high number of simultaneous connections, keeping our busy world connected. So that's how your mobile phone communicates, from the moment you dial a number to the moment your call is connected. It's quite a journey, isn't it? Journey.